Hello, everyone. Today we're going to talk about two phenomena that we don't normally think of as related, the binding problem and the physics of black holes. But these actually have remarkably similar properties, and we think black holes hold the key to understanding the binding problem. Let's first recap what the binding problem is. So the visual cortex has now been completely mapped, and we know that there's no full representation of the external world that exists at the neuronal level. In other words, there's no movie screen of neurons that is what you are seeing right now. The perceptual information is processed all over the brain, different regions, different properties, and somehow information from these different regions is integrated together to form the subjective unity of experience is our just awareness. And obviously features are attached to objects and properties of objects and all of that stuff happens, but there is no movie screen, at least at the neuronal level. A lot of neuroscientists believe that the reality we perceive is the simplest possible explanation for the perceptual data that the brain collects. Why I'm emphasizing simple as possible will become important later in the talk, but I want to note it here because it's pretty important. What does this mean, though? So let's construct a thought experiment to illustrate the point with like ChatGPT. It's pretty popular these days. So suppose there are 1,000 people in a lecture hall, and everyone in it types 10,000 keywords of what they are perceiving around them into ChatGPT and asks it to construct a narrative with those words. What are the chances that all 1,000 people construct the same narrative? Now imagine the chances if instead of a worded story, we use generative AI to generate a movie experience in 3D plus the other senses. The only way for all 1,000 people to construct that same movie is if this generative AI is finding a global solution rather than a local one. If it were local, everyone in the lecture hall would likely perceive a different reality. But they don't, so it has to be a global solution so everyone can kind of conclude the same thing. Why does a global solution mean simple as possible? Why couldn't it be a global solution to another problem? And to see that, just think of Occam's razor, that if we're trying to explain the world, we're looking for the simplest explanation. For some folks, it's easier to think of this rendering a bitmap image, a raw video file of the world into a vector graphics. You're kind of decomposing the image into its component objects, its component parts, and their properties. It's much simpler, much shorter, smaller data file to describe the world that way than it is as a raw image file. All right, so let's now move on to talking about black holes. So one of the hottest topics in theoretical physics these days is this ADSCFT conjecture. And the reason it's hot is because it is a way to unify gravity with quantum field theory. And what you do is ADS stands for anti-de Sitter space, and it's the space here you see in this picture. And the idea with it is this could be like the kind of geometry that describes the inside of a black hole, where this boundary is infinitely far away. It's bounded region, but if you keep traveling closer and closer and closer to the boundary, space gets smaller and smaller and smaller, and you never quite reach the boundary. And the reason this is chosen is to create a toy model where the math is easy to work out. Because what you can do is then you can put this quantum field theory, you can have a whole bunch of quantum information on the boundary, and it's infinitely far away, so it doesn't disturb the gravitational space in the inside called the bulk. And what ADS-CFT scientists have discovered, physicists, is that there's a whole bunch of parallels between what happens on the boundary and what happens on the inside of the bulk. What happens on the boundary is a quantum field theory. What happens on the inside is a theory of gravity, like general relativity. And you can do calculations on the boundary, or you can do an equivalent calculation in the bulk and always get the same answer. And that works for many, many, many different things. So there's like a dictionary that translates, hey, this on the boundary corresponds to this in the bulk. So what does this ADSCFT conjecture have to do with the binding problem? Well, so a lot of similarities jump out at us. For example, this space, the bulk inside, integrates information from all across the boundary. Just like in the binding problem, we integrate information from throughout the brain. Specifically, at each point in space, in the bulk, in the interior, that point is like a hologram. It is contributed to by a wide region of the surface of the system. And the further you get into the interior, into the bulk, the more broadly the information is integrated, such that at the center, the entire boundary is contributing to the geometry of space-time at that point in the bulk. So this is a candidate for integration of information into a single subjective unity of experience type of experience. This geometry is combining that information just like we need it to for the binding problem. And then we can say some more things. So some aspects of the geometry in an ADSC system, and I won't get into the details of what, but certain aspects of the geometry are driven by the complexity of the information. In other words, it's technically the simplest quantum circuit that will sort out or reproduce that information on the boundary is related to a certain aspect of the geometry in the bulk. When we're talking about a complexity problem, that means we're finding the simplest possible quantum circuit, the simplest possible description of that information on the boundary. But there again, that's just like the binding problem, where there's an argument to say, hey, the reality we perceive is the simplest explanation of all the perceptual data that you're receiving right now. So this complexity problem is very important because this is kind of a smoking gun. It's a very, very hard problem to solve. Essentially the classical version is you have a string of zeros and ones, and you have sort of logical gate operators that can flip bits from 0 to 1. And you say, assume they start out all zeros. What's the simplest set of gates that will, recreate this string of ones and zeros? And, that's a very, very, very hard problem to solve. And so it's in the category computational complexity category called NP. And that means that, you can't, for practical purposes, solve it on a conventional computer, can't solve it on a laptop, can't solve it on a mainframe or server. The complexity problems are not thought to be in BQP. And then set BQP is all the things you can solve with a quantum computer, in reasonable time. Complexity problems are not thought to be in that set either. So this ADSCFT system is the only system that can sort out the complexity of this information in real time, or anything close to real time. So that's why this is a smoking gun, that if what the reality we're perceiving is really the simplest possible explanation of perceptual data, only this system can solve that problem. So does all this mean that we are a black hole? The answer is no to that. This sort of ADS-CFT is an approximation, but this sort of physics seems to apply in systems right here on Earth. For example, superfluids and superconductors exhibit the same sort of behavior as expected from an ADS-CFT system. So even a black hole can be thought of as a kind of superfluid. So just like superfluid helium in the lab. And also even just with a quantum computer, you can entangle 24 qubits. The qubits act like 24 qubits on the boundary, and you can play around with those. There was an article from, I think, some researchers at MIT a few months back where they entangled some qubits on the boundary and teleported a quantum state from one side to the other. And this has a physical description or a gravitational description equivalent to transporting that quantum information through a wormhole, through the bulk in the interior. And Leonard Susskind is a physicist at Stanford that's working on this kind of thing and kind of leading that charge. But yes, it seems to be applicable to systems right here on Earth. Now, superfluids that take especially cold temperatures and special conditions to run, and same thing with a quantum computer. What kind of system in the body could house this sort of physics? And for a long while, we've known about a system called a Freilich condensate, which is a quantum system that can exist in its quantum states even at biological temperatures. The key that makes that happen is energy is constantly pumped into the system, and that helps the system avoid decoherence and that kind of thing. The Freilich condensate's been known about or been proposed more than 50 years ago, but it took a long time to find evidence of one, and so a lot of physicists grew skeptical that would could exist. But there was a paper a few years back where a team witnessed a Freilich condensate in a protein called albumin, I believe. I think that's egg white, and it was under exposure to a terahertz laser, but it opens the possibility that Freilich condensate can exist in the body, and these quantum coherent states can be there. And then we have this sort of physics applicable to a system in a biological organism. So let's go ahead and walk through an example of what we're talking about. Here in front of you is a common illusion, if you can call it that. But as you can probably guess, if you've seen these before, the square labeled A and square labeled B are actually the exact same shade of gray. You can cover up the image if you'd like to prove that to yourself, but it's easy enough to do. But the idea is that, information here, this whole image is captured, and that information is integrated to come up with a gravitational representation, and then that gravitational information representation is mapped onto subjective experience. So space-time comes up with this explanation that, hey, cell B is, in a shadow from the green tower, and after all that processing takes place, then we map, gravity. The hologram simplifies that, and then we map that gravitational experience, that gravitational geometry onto a subjective experience. So it makes the mapping of the physical onto the subjective much simpler, because gravity is doing the heavy lifting of decoding the information for us. So it's natural to ask the question next, which is, if a superfluid or a Freilich condensate all by itself can have perceptual awareness, what do you need neurons for? And obviously models of neurons do a lot of things like object recognition, like all the stuff going on in machine learning, artificial intelligence. So the thing about these systems is that they evolve really, really quickly. And so it's unlikely, for example, a black hole would come to thermal equilibrium in timescales under a millisecond. So all this information and geometries resolve very fast. I don't think a system like a superfluid or Freilich condensate in itself has any mechanism of memory. In other words, ways to remember what was going on even a millisecond ago. It's just sort of like pure awareness. And so I think what happens is that neurons provide that mechanism to persist quantum information through a kind of a, classical firing process, classical size objects, but maintain that quantum tail of information. Uh, and that allows the system, to remember what happened moments ago and so on and so forth. But that's just a guess. And, I have to think about that some more. So let's recap our argument and discuss what would be needed to consider this argument a proof that the physics of ADS-CFT systems was indeed what gives rise to binding and subjective experience in the binding problem. So we assumed that the reality we experience, as described in the binding problem, is the simplest possible explanation of perceptual data. We gave kind of an argument for that, but that's not known. But if that's true, then in subjective experience, we're talking about a complexity problem, finding the simplest possible explanation. We assumed that ADS-CFT is correct. That also is not known. It presently has the status of a well-supported conjecture. And then within ADS-CFT is what's called Susskind's conjecture, and that was where complexity is introduced into that model, like complexity equals volume or that kind of stuff. That also has some strong support, but it's not proven. And then lastly, that minimum quantum circuit complexity can be mapped onto subjective simplicity. But again, if the laws of physics are, if they're complete and everything is physical and can be mapped on to the subjective, in other words, there's nothing outside the physical, then the only known physical system that can solve a complexity problem is this ADS-CFT and Susskind's conjecture in particular. So it's the only thing that could give rise to subjective experience, and we'd have to go through the ordeal of mapping one onto the other. But it could, in principle, it must be the solution because of its computational complexity in nature. So what does all this mean? It means that whenever we see a strongly coupled system, like a superfluid or a black hole or a superconductor or a Froelich condensate or something like that in a biological organism, those systems are aware. They're perceiving the world around them. They don't necessarily have any mechanism for memory, but they are aware. Probably inside your body, what's giving rise to this phenomena is something like a Froelich condensate or something similar. It curves just as space-time curves to sort out the complexity, the patterns in that quantum information. That is the act of you perceiving the surrounding world. These things happen two sides of the same coin at the same time. So locate your seat of awareness in the space-time itself. So your body is not passing through or existing in space. It is coupled to the fabric of space-time itself. And what you're perceiving is encoded in the space-time inside you. There is a movement going on called It from Qubit, and what this movement is in the physics community. And it has to do with the idea that all space emerges from quantum entanglement. It is space-time, qubit is quantum information. So it looks like what that means for us is that awareness also emerges at the same time. Space and awareness go together. And so it means that the sort of awareness of this universe started not with higher level living creatures on Earth, but at the dawn of the universe kind of thing. As soon as there was space, there was awareness. And it also suggests this universe itself is aware. What it is aware of would be encoded in the geometry of space-time, and it probably corresponds to the information on its boundary. Interesting stuff. That's the end. Thanks for watching, folks. If you have any questions, please don't hesitate to reach out. I'll put my email on the screen. We talked about a lot of radical ideas here today, but I hope that you give them some thought. And like I said, don't hesitate to ask questions. Thank you. Have a great day. Bye.